In the previous video, I showed you how to find the electronic version of your textbook inside my math lab. I'm going to use example 7 from page 168 as the example for this video. Example 7 asks us to graph this piecewise function. When reading a piecewise function, it's important to understand that the information given after the if represents the domain for this piece of the function. So when x values are less than or equal to 1, I would use this function to generate the outputs. When the x values are greater than 1, I would use the bottom line to generate the output values. The easiest way to graph a piecewise function is to simply make a table of values. So that's what I'm going to do first. All right, what I have done is set up two tables of values, one for each piece of the function. In particular, you'll notice that the leftmost column is where I choose x values to substitute into my function. The middle section is where I show that substitution. And then the last column is where I summarize my results. Now, I did write here the domain for the first function. The domain was anything less than or equal to 1. So I'm going to start with the x value of 1 because I'm allowed to equal 1. I'm going to say that f of 1 equals, substitute 1 plus 2, and that equals 3. And in the last column, I take that x input, which was 1, and the corresponding output from the middle section, which was 3. This gives me a point to plot to make the graph. You would continue choosing other x values that are less than 1. And there's no reason to choose decimals here. You might as well stick with the whole numbers, make the calculations easier. In your table, you're going to want to choose 5 or 6 different x values. Once you've done that, you would now switch and create the table for the second part of the piecewise function. In this case, x is not allowed to equal 1. X is only allowed to be numbers that are bigger than 1. I'm going to leave a little space up here. I'm going to pick the first whole number bigger than 1, which is 2. And in this instance, there is no place to substitute a 2 on the right-hand side. This is a constant function. No matter what the input is, it always outputs 4. So this table is pretty quick to generate. I'm going to continue picking numbers bigger than 1. Once again, I would recommend a minimum of 5 or 6 x values in your table. Now, I did leave a space above 2 in this case. X greater than 1 means x can be any number really, really close to 1, but it can't equal 1. And to help me get this graph to be accurate, I'm going to want to choose something that's just a little bit above 1. I'm going to use 1.5. Still gives me an output of 4. And again, once you have 5 or 6 values in your table, you're ready to graph. Here's what the completed first table should look like, and the completed second table. Now you would begin plotting the points from your table. So you would set up an x and y axis and begin plotting points. All right, I went ahead and plotted the 6 points from the first table, f of x equals x plus 2. And we can kind of see what shape is happening here. This looks very much like a line. Well, it is. The domain of this line was all x values less than or equal to 1. So when I connect up these points, I would start at 1 and go in the direction of the values that are less than 1. So here's what this portion of the graph looks like. And it would be appropriate to put an arrow on this end of the graph to show that it continues going in this direction. Now I need to plot the points from the other table. As you can see, I have plotted the 5 values from the table. The domain for this function, f of x equals 4, Was any value greater than 1? That means this shape should start approximately here and then continue off to the right as a horizontal line because it is a constant function. But what should I put here? I can't put a closed dot at 1 because I'm not allowed to equal 1. But I am allowed to equal like 1.1, 1.2. When you have a strictly greater than sign without the equal to underneath, we saw this previously. The correct thing to do is to use an open circle at this point. This indicates that I can get very, very close to this value, but I will never equal this value. And now I'll go ahead and connect those dots. Okay, I drew my line through the points, and again, it would be appropriate on the right edge of this graph to put an arrow indicating it continues forever in this direction. This is the graph of our piecewise function f of x. The portion on the left represents f of x equals x plus 2 for all values less than or equal to 1. The right-hand piece represents all the function values for f of x equals 4 for x values greater than 1. Here's what a sample MyMathLab problem would look like. We're told that the domain for this piecewise function is everything. We're asked to graph the function and then use the graph to determine the function's range. Okay, here's my piecewise function, and just like you have seen earlier in this video, the thing you want to do is set up some tables of values. All right, you can see I've set up two tables again, one for each branch of the piecewise function. I'm going to go to the first table, and the domain for this function was all x values less than or equal to 0. So I'm allowed to equal 0. I would use that as an input, substitute in the middle section, and then write the input and output together. There's my first point. I would continue doing this, choosing x values that are less than 0. I would do the same process for the second table. In this case, x must be greater than 0. So I can't start at 0. The first whole number I can start at is 1. And again, I'm leaving a little bit of space here intentionally. F of 1, another constant function, is 2, so it's always going to output 2. I pick more x values bigger than 1, and same as last time, we're going to choose a value that's in between 1 and 0, just to give us that little extra information. I'm going to use 0.5. I'm going to assume that you could take it from here, get your 5 or 6 values per table. Now we're ready to start looking at the graph and comparing. The first point that exists is the point 0, 0. So I look at all my choices. Letter A has a closed dot at 0, 0, so this is a possibility. Choice B is an open circle. That's incorrect. The point 0, 0 does exist. Closed circle in choice C, open circle in choice D. So I've narrowed down my choices already. Now, the next point is -1, comma, -5. I look at choice A, -1, -5 should be down here on the graph. So I don't think this is right. So now looking at choice C, okay, yeah, it seems like -1, -5 is accurate. Keep in mind here the scale is going out to 10, so each of these little marks is 2 units. So this is the correct blue portion of the graph. For my purple table, I would look for the points 1, 2, 2, 2, 3, 2. Yep, that seems to be here. And there is an open circle at this end because we have a strictly greater than. Whenever there's a strictly greater than or a strictly less than, no equal to signs on them, we must use an open circle. So the correct answer to this question is going to be C. Now I'm asked to give the range. I'm going to type my answer using interval notation, set notation, and the union operator as needed. They are asking you to indicate what the set of outputs is going to look like. The range is the y values, the set of outputs. One way to find that is to scan the y coordinates in your tables. Another way to find it is to look at the graph and try to name lowest to highest y values. Now the graph is going to keep going in this direction. So the lowest value for this branch of the graph is going to be negative infinity. The highest y value that appears on this branch is 0. And I can equal 0, so I would use a square bracket here. Now notice this little portion between 0 and 2 does not feature any blue part of the function. The function jumps. We actually call that a jump discontinuity. The function picks up again here, and it equals 2 the whole rest of the way. We're going to use the union operator as a way of saying my range is this first interval, union, together with, and there's just a single value here. When you have an output that's a single value, we don't use interval notation. We now use set notation, which means set brackets, and put that one value inside. Again, the only reason we're doing this is because this is a constant function. The y values are always 2 on this stretch of the graph. This is the proper way to show that. So that would be your answer for the range. One last note. When you're doing a problem like this in my math lab, as soon as you click inside the range box, inside the answer box, you will see the palette show up at the bottom of your screen. This is where you would find the union symbol.